we're going to move on now with more inverse trigonometric functions. We're going to look at the cotangent, inverse cotangent that is, arc cotangent, and we're going to look at the cosecant, and then we're going to take a look at the integration by parts methodology. So we've already looked at, I believe we did the inverse tangent, we did the secant, we did sine, cosine, so we did 4. We got the last 2 trigonometric, inverse trigonometric functions to do, and then we will move on to a new method. So here we say that the cotangent y equals u. We draw our right triangle, our angle y, and the cotangent. Now, cotangent is cosine x on sine x. So here we have A, R, B, and we have A and R on B on R. And these cancel, and we have A on B. And that is equal to u. So this is u, this is 1, and this one is square root of 1 plus u squared. So now we take the derivative of the cotangent, and cotangent again is cosine of x over sine of x. So if we say d dx of cosine x on sine x, we have, just to save room, we have minus sine x on sine x plus cosine x times -1 times sine x squared cosine x. And that equals minus 1 minus cotangent squared x. But then when we go to our identities, cosine squared x plus sine squared x equals 1, we have, when we divide through by sine squared x plus, whoops, I shouldn't have done that. I don't know why I did that. Okay, this, there we go. by sine squared x equals, whoops, what am I doing? Equals 1 over sine squared x. And that is equal to cotangent squared x plus 1 equals cosecant squared x. And so, where did we go wrong? We didn't. This is equal to negative cosecant squared x. So, when we take the derivative of cotangent y, we have, I'm going to try and keep these separate. Now, we have the minus cosecant squared y dy dx equals d du of u, and then dy dx dx equals 1 over the minus cosecant squared x. And cosecant squared is cosecant of y equals 1 plus u squared, because it's r over b. So we have dy dx equals d du of cotangent of u, arccotangent of u. So we have d du equals minus 1 over the cosecant squared, so that's 1 over, and it's the square, so it's 1 plus u squared. And let me do this right. Glad this has an eraser. D du of cotangent, arccotangent of u equals, there we go. So that's our derivative. Now, if we multiply across, we got d arccotangent u equals minus du over 1 plus u squared. And then if we take our integral, we have swapping sides. We got du 1 plus u squared equals cotangent, arccotangent of u plus c. And that's let's see how we have this. Yeah, that's the correct answer. I wasn't able to read it very well. And if we do this, multiply cross by -1, we got cotangent -1 plus minus c, or plus c prime. It doesn't matter. Okay, therefore we got another derivative, another integral here that leads to an arc cosine or cotangent result. Pretty neat stuff. And so now we're on our last arc trigonometric function, and that's the cosecant. So we have y equals cosecant, arc cosecant of u, and then cosecant of y equals u, and then we do our little triangle, and A, B, R, and the cosecant is cosecant. Boy, I don't know why this does this every so often. I gotta cosecant of x equals 1 over the sine of x. So that's R on B, and that's equal to U. So R equals U, B equals 1, and A equals the square root of 1. Oh, let's see. We got A squared plus B squared equals R squared equals U squared. B is 1. A squared plus 1. So we have U squared minus 1 equals A squared. So U squared minus 1. And that's what we have. U squared minus 1, 1, U. And this is y. Now, we go through our procedure. We go cosecant x equals 1, or sine of 1, let's say sine negative x, and so dx cosecant x equals minus sine squared x cos x, and that's equal to cotangent minus cotangent x cosecant x. So now we take the derivative, and we have minus cotangent x, or not x, u. Okay, y cosecant y dy du equals du du. So dy du equals minus 1 over cotangent y and cosecant y. And that's also equal to d du of cosecant arc cosecant of u. And now we go back to our right triangle, fill it in. Let's swap sides. D du cosecant arc cosecant of u equals minus 1 over cotangent of u, and cotangent is a over b, which is u squared minus 1. Okay, and cosecant is r over b, which is u. So this is u times the square root of u squared minus 1. And now we just multiply across by du, and we've got d cosecant, arc cosecant of u equals minus du over u square root of u squared minus 1. And then we take our integrals, and we have, we'll swap things around, minus du on u square root of u squared minus 1 equals cosecant, arc cosecant of u plus c. Or we can say du on u squared minus 1 equals minus cosecant, arc cosecant u plus c. And we have our final results. It's a pretty cool method when you stop and think about it. I mean, it's really quite beautiful when you stop and think about the whole process and how you go through it methodically to come up with the final answer. I just think it's absolutely fantastic. It just has a beauty to it, a flow that is so natural and so neat. And you can apply this method, when you if you go into the handbook, oops, gotta get my pen, the handbook of physics and chemistry, the first section, or one of the early sections in the book, is math. They have differentials, derivatives, and they have integrals. And what they do is they give you this. They give you the final form. If you have an integrand of this form, then you have a result like that. And just don't have the intuitive sense of how you got there. I mean, how do you go from a polynomial, integrand, to an arc trigonometric function? And it just doesn't seem intuitive. But when you work this out just the way we did here, then you can see how it comes out and what the relationship is and how beautiful that is. It really is. There's a beauty to it. So we'll close out that section, and we're going to take a look at a whole new methodology. And this methodology, just a minute. This methodology is quite interesting in itself. I mentioned it before, and we start out with d u v. Whoops, my spastic hand. Is equal to u dv plus v du. And then if you take the integral of uv you have uv equals v du plus u dv, and then swapping sides around and doing a little algebra, we have v du is equal to u v minus u dv. And that's what we call integration by parts. Integration by parts, where we have d u v equals u dv plus v du. And uv equals u dv plus v du. And we're going to take a look at the case where u equals the arctan of x. That means tangent u equals x. And that means if we draw our right triangle, u, so tangent u is b, a, and r, where b on a equals x on 1, so r equals 1 plus x squared. And we have, as we've seen before, this is secant squared u du dx equals dx of x, and we have du dx equals 1 over the secant squared of u, and that would be equal to square root of 1 plus x, well, no, not square root, what am I doing? It's the square you see the secant is r over a, and r is the square root of 1, but we got square, so we have 1 plus x squared. And that means that cosecant, cosine of u is equal to 1 over 1 plus x squared. So let's say in our situation u equals the arctan of x, and we say v is x, and we have dv equals dx, dv equals dx, and du equals du equals dx over 1 plus x squared. So we say uv equals x arctan of u, and this is equal to arctan of x dx plus u du, let's see, u dv, which is x, or v du actually, which would be x dx on 1 plus x squared. So we say that our integral of the arctan of x dx is equal to x arctan of x minus x dx on 1 plus x squared. And then if we do a p substitution, or let's say z or whatever, we say z equals 1 plus x squared. Yeah, I made a mistake here. Sorry. I gotta fix this. Alright. Just noticed that. Okay, so now we say dz equals 2x dx, and x dx equals dz on 2. So we have equals x arctan of x minus, now we have 1/2 1 over u. We got dz over z. And that we know is the Lin function. So tan negative 1x minus 1/2 ln z plus some constant, and then we have x tangent arctangent x minus, and we put the correct integrand or argument in, ln 1 plus x squared plus c. And so we have a whole new integral using that really cool method. This is really, really neat. Let's see if I got it right. So this is the kind of integral that you'll see in the handbook of physics and chemistry. But that's really, really cool. And that's because of this approach. We can do another one using the integration by parts. Let's take a look at the arc cosine. Whoops, what did I do that for? That's what I meant to do. Alright. So, here we go. We're going to use the integration by parts. The uv equals u dv plus v du. And in this case, we have u equals cosine, the arc cosine of x. So cosine of u equals x. That means if we draw our right triangle, we have R, A, B, and R equals x. So A equals x, R equals 1, and B equals, and we have a squared plus b squared equals r squared. But if a is x plus b squared equals 1, b squared equals 1 minus x squared, and so this is 1 minus x squared, square root. So now that we're set, mu, we have u equals the arc cosine of x, and the du, and we know that this is minus sine u du dx equals d dx of x, and dy dx equals 1 over minus sine of u and so du, let's see. I'm sorry, I made a mistake here. Du, not dy dx, that's where I got confused. Du dx. So du equals 1 over minus sine of u, or sine of x. Let's see, wait a second before I go too far. My pen. Okay. And that is equal to 1 over minus 1 over 1 minus x squared. So du dx, du equals minus 1 over 1 minus x squared dx, and v equals x, and dv equals dx. Okay, so uv is x cosine, arc cosine of x minus u dv. All right, u dv let's say equals u dv plus v du, and u dv, we do our substitution. U dv is cosine, arc cosine of x, dv is dx, plus v x du, which is minus dx over square root of 1 minus x squared. So now we rearrange things and we say that the integral of the arcsine dx is equal to x inverse cosine of x minus, but that is a minus, so that's plus x dx on square root of 1 minus x squared. And then we use another substitution. We say k equals 1 minus x squared dk equals 2x dx. So we have x cosine, arc cosine of x plus 1/2 dk over k to the 1/2. And that's basically k to the minus 1/2. So we have x cos minus arc cos plus 1/2 k to the minus 1/2 dk, and that's equal to x cosine, arc cosine of x plus 1/2 over x, and this is k to the 1/2 over 1/2, and so that's equal to x arc cosine of x, and this is equal to k, or whoops, I shouldn't have, plus k to the 1/2, but k to the 1/2 is 1 plus x squared, and c. So here we have our check one thing on what we did before. I think I may have screwed up. Oh no, I did it right. I thought I had left the 1/2 out. So that is correct. Everything is copacetic. That's a pretty cool method that allows you to do integrals that you wouldn't think that you'd be able to do. So we did the arc cosine. We could do the same thing for the arc sine. So I think we'll go ahead and do it. Oh my. I just got to answer a quick text. Sorry, guys. I'm going in for heart surgery tomorrow, and I'm a little on the nervous side. So my kids are trying to make me feel a little better. All right, so let's take a look at how this method allows us to find the integrals of the inverse trigonometric functions. So we say u equals the arc sine of x, and sine u equals x. And then we make our triangle just like we have over and over again. This is u, and then sine of x is sine of u is x, so we have a, b, r, and b on r equals x. So we have b equals x, r equals 1, and a squared, so we got a squared plus b squared equals r squared. And we know that b is x, r is 1, so a equals the square root of 1 minus x squared. Then we do our differentiation. We do cosine u du dx equals d dx of x, so du dx equals 1 over the cosine of u. That's the secant. And the secant is r over a, and that's 1 over 1 minus x squared. So we have 1 over 1 minus x squared. So here we say u equals the arc sine of x. This is u, du, I keep forgetting. All right, du, I always think in terms of y. You got to be careful with that. Du dx, that looks like a y again. Du dx equals 1 over the square root of 1 minus x squared. V equals x, dv equals dx. So we have uv equals u dv plus v du. And uv is x arc sine of x equals u. So this is the arc sine of x dx plus, and u, v is x, and du is dx over square root of 1 minus x squared. So let's say k equals 1 minus x squared, dk equals minus 2x dx. And so we have, let's get swapping around with things. We have sine, the arc sine of x dx equals x arc sine of x minus x dx on square root of 1 minus x squared. But k is 1 minus x squared, and dk is minus 2 dx, so x dx equals, or let's say minus x dx equals dk. Ah, boy, that is one spastic k. Oh, man, my wrists. Whoops. My wrist sometimes doesn't do what I want it to do. Okay, dk on 2. So we do have this exactly. We have x arc sine of x, we plus, all right, 1/2 k dk on k to the 1/2, and that's simply x arc sine of x plus 1/2 k to the minus 1/2 dk, and that is x sine, arc sine of x plus 1/2. Now this we have k to the 1/2 on 1/2, so these cancel, and plus c, and this equals x sine, arc sine of x plus k. Now k is 1 minus x squared, so we have square root of 1 minus x squared plus c, and that's what this, okay, there we go. Arc sine of x dx, and that's our integral. And I have this kind of, it's a little sloppy, so it's a little hard to read, so I'm going to take these out and then just redraw it so that it's there we go. And this, we don't need that. There we go. And that's a little neater. And now this is our end result. And we have the integral of the arc sine. And you know, it's pretty complicated. I mean, when you stop and you think about it, look at this result, and what we did, how we thought through this process all the way down to get to that result. It's and the key to the whole thing is how you pick your U and your V. That is key, is knowing how to pick your U and your V. Makes it simpler if you choose it correctly. It may make it so that it's impossible to figure out otherwise. So it takes a little practice in order to get it straight. So we'll leave this up for you just for a little bit so that you can see the end result and the process of how we got there. And now we're going to do another one. We're going to look at the cotangent. And again, that's a bit involved, but it's fun. It's cool stuff. Really, really cool. So we start out with u equals the cotangent or arc cotangent of x, which means that the cotangent of u equals x. And we do our little, boy, not good there. Our little right triangle. And we got A, B, and R, and B. So cotangent is cosine x on sine x, and that is A on B. So we have A equals x, B equals 1, and R equals 1 plus x squared, square root. So again, we take our derivative, which we know from the past experience is the negative cosecant squared of x, or of u, du dx equals d dx of x. And so du dx equals 1 over, or negative 1, over cosecant squared of u, and u, and the cosecant squared is r on b. That's the cosecant of u. So we have minus r on u, so we have, or r on b, so we have 1 plus x squared, and that's a negative. So that's du dx. So we've picked our u equals cotangent, or the arc cotangent of x. Du equals minus 1 plus, hang on a second. Let's check this out first. Okay. Cosecant is r on b. R is that. Okay. So cosecant squared is this squared. So that's minus 1 plus x squared. but it's R on B is this 1 plus x squared. So yeah, this is 1 on, 1 on. All right, so we made a mistake here. You have to be careful with these things. So where my mistake was, before we go any further, I just wanted to show you. Now, R on B is the square root of 1 plus x squared. But we have 1 on cosecant squared. See? So then that goes there. And this is squared, so that's got to be squared. So this is minus 1 on 1 plus x squared. So du equals minus 1 on 1 plus x squared dx. V equals x and dv equals dx. So now we've got all our parameters. So uv is x, cotangent, arc cotangent of x equals u dv plus v du, and that is u dv is cotangent, arc cotangent x dx plus, now v x du, and du is minus dx on 1 plus x squared. Okay, so we can move things around, and we got the integral of the arc cotangent of x dx equals x arc cotangent of x minus x dx on 1 plus x squared. So we make a substitution. We go k equals 1 plus x squared, dk equals 2x dx, and x dx equals dk on 2. So we've got x arc cotangent x minus 1/2, and we have x dx, so that's dk on k, and that happens to be x cotangent, arc cotangent x minus 1/2 ln k plus c. Now we put our argument back in, and we have the integral of the arc cotangent of x dx equals x arc cotangent of x minus 1/2 the natural log of 1 plus x squared plus c. And that is our final result. And you wouldn't think, when you looked at the Handbook of Physics, how in the world do they come back with these answers? because this is all they give you. When you look at the handbook of chemistry and physics, they'll give you a result like this, and you wouldn't have any ghost of an idea of how you arrived at that point. But thinking through the process, using the UV, UdV plus VdU methodology really works. It's such a powerful tool. And even with such a tool, you have difficulty with many different integrals that can't be solved. As I mentioned, more integrals are not doable than doable. So what's next? Okay, now we're going to do the integral of the inverse secant using the method of integrating by parts. And this one's going to be a bit complicated. This one's going to be a little bit long, and we're going to be doing this in several parts. So first, we're going to start out as we always do, and then we have secant of u equals x, and we make our right triangle, and u, and a, b, r, and secant is r over a, and that's x, so that means r is x, a is 1, and b is square root of x squared minus 1. So then we take our derivatives. We got secant u tan u du dx equals d dx of x, and dy dx equals 1 over the secant of u and tangent of u, and that equals 1 over, now we have secant is x, and tangent, we got a being 1, so b over a, that leaves us with x squared minus 1. So we pick our uv. U equals secant minus 1 of x, du equals dx on x, square root of x squared minus 1, v equals x, and dv equals dx. And then we use our uv. V equals the integral of v du plus integral of u dv. And in that case, this is x, arc secant of x equals, and v du, so we have x dx over x square root of x squared minus 1 plus the integral of the arc secant of x dx. And now we just move things around a little bit algebraically to make it a little simpler. We have secant, arc secant of x dx is equal to x arc secant x, and this is minus, and these x's cancel out, so we end up with dx over square root of x squared minus 1. Now we're going to do something that we haven't done before, and we're going to use a trigonometric substitution, and we're going to say that that x is equal to secant theta. That means dx equals secant theta tan theta d theta. That's from our derivatives. And we did this derivative back in the trigonometric derivatives. Okay, so now we have a new line, secant, arc secant x dx equals x arc secant x, and that's minus. Now what we have here is secant theta tan theta over secant squared theta minus 1. That's secant squared. And we know that from the I got a trouble with the door here staying shut. We're gonna just take 1 second, shut the window so I don't have the problem with airflow opening and slamming of the door. Okay, now we know that from trigonometric identities that we have the cosine squared x plus sine squared x equals 1, and if we divide by cosine squared x all across, we end up with 1 plus tan squared x equals secant squared, or theta, and secant squared theta minus 1 is tangent squared theta. So now we have down here, we have in the denominator the square root of tan squared theta, and that is simply tan theta, and then that crosses out with this, because this is tangent theta. So now all we have is secant, the arc secant of x dx equals x secant or arcsecant x minus, now we have the integral of secant theta d theta. Now remember, this is a substitute that we made up here. And so what we're going to do is we're going to save this screen. So we have secant theta d theta, and that's the integral that we're interested in. So if we multiply, we go secant theta times secant theta plus tangent theta boy, this sometimes does that, I don't know why, over secant theta plus tangent theta and d theta. We know that this ratio is 1, but that allows us to have an integrand that we can substitute. So secant theta, okay, plus secant theta tan theta, we're just multiplying through, over secant theta plus tangent theta d theta. And if we did a u equals secant theta plus tan theta, then du equals secant theta tan theta plus secant squared theta, and that's all d theta. So we have here, in essence, du over u, and that's equal to ln u plus c. Then we substitute back in. Let's make that bracket square. We got u, which is secant theta plus tangent theta plus c. Now that's what secant theta d theta, that's the integral for that. So now we can go back to our other and so we have the arc secant of x dx equals x arc secant of x minus, and now we know what the integral there, we solved that, that's the ln of secant theta plus tangent theta plus c. But remember, x was secant theta. So we have secant theta is x1 and x squared minus 1. So we substitute that back in, and our final answer is C for the arc secant of x dx. We have x arc secant of x minus the ln of x plus square root of x squared minus 1 plus c. And that's our answer. It took a while getting there, but we went through every step and we derived the answer. And now we got a bunch of cutting we got to do. This is our last one for today.